All right, welcome everyone to the final presentations of the AI for Bears Challenge. Over the last 10 weeks, we worked from a data problem to an AI solution with a team of 20 AI engineers. We've had a blast. I think we have some very cool results to share with you today. I'll start off with an introduction, but before we get started, I really want to say our thank yous to the Bear ID project and especially Ed and Melanie who are here today with us for hosting this challenge with us. And of course, not to forget from Hectic Planet, Thijs, welcome. Thanks so much for joining and organizing this challenge with us. Also, a quick thank you to ARM, NXP, and Edge Impulse for further helping us organize this challenge with their expertise in hardware that we could use, hardware and software that we could use in order to bring this challenge to a success. For everyone who doesn't know us yet, my name is Dorian. I'm a challenge manager for Fruitbench AI, and I will quickly explain what we are doing today in the challenge introduction. You will hear from 4 of our teams who worked on classification on chip, face detection, and segmentation. Team 3 was focusing on bear identification, and the last team tried to integrate everything as a pipeline on our edge devices. At the end, I've left some time for Thijs, Ed, and Melanie to give some final words, but we'll get to that in the last minutes of the presentation. If you have any questions throughout the presentation, please put them in chat, or you can raise your hand in the bottom of your screen by using the hand icon. I will try to attend to those questions at suiting moments, but we'll also have a Q&A in the end of the presentation. So for everyone who's new here and who doesn't know us yet, we are Fruitbench AI and we are a global AI for good community. And we have started this community because we believe that to solve humanity's greatest challenges, we need to educate AI engineers at scale with an ethical and sustainable mindset. The way that we do this is by organizing AI for good challenges. And how we define AI for good is basically by linking our challenges to one of the sustainable development goals. For this challenge, we focus on wildlife and bears specific, which is one of the sustainable development goals called Life on Land. It focuses on biodiversity, and it's one of the main topics that we organize our challenges in and we're very passionate about. Our challenges are, besides aiming for a global good, they are also a very good way to learn in a peer-to-peer fashion. We offer challenge-based learning as well as mentorship tracks where you can join and really learn how to apply AI in the real world. For today, we're going to talk about the AI for Bears challenge, and it's basically 2 challenges that we tried to solve in the last 10 weeks. The first one is bear detection on edge, and this is the challenge we tried to solve together with Hectic Planet. And this challenge is important that we train energy efficient models that can run on smaller edge devices capable of accurately classifying if there is a bear seen on a camera trap or on a radar camera, in order to be able to set off an alarm using air dancers. It's called, if I'm correct. And an air dancer is what you guys probably know as some kind of commercial thing. It's basically one of the blow-up dolls that goes all the way like this in order to scare off a bear, and as well to set off an alarm in order to avoid human-bear conflict. The second challenge we try to solve is together with the Bear ID project, and specifically with Melanie and Ed, where we try to identify and re-identify bears based on face chips. So this part of the challenge was cut up in 3 teams. The first team focused on face detection and segmentation, basically to cut out only the bear face and to remove all the other noise in the image. The second team tried to build algorithms capable of detecting features in the bear face that could be recognized and could be compared to other bears in the dataset. And by using these algorithms, we can help the researchers monitor the bear population for their project in British Columbia. But in essence, it could, of course, help bear monitoring worldwide. The last team focused on trying to get all the algorithms that we built on the NXP chips. Yeah, so the main goals: create efficient classification models that can run on edge devices and create bear recognition models to identify and re-identify bears. As I said, it was 10 weeks, 4 working groups, 19 AI for Good engineers who've put in a combined effort of 1,500 hours or even more. And I'm very proud to introduce to you guys Davide Coppola. He is the first presenter of today, and he will be presenting the classification on edge part.
Okay. Hello, everyone. I will be presenting for the classification on chip team. This is a very small team where John and I worked on the classification model, and then we had help from Gaspard and Jesse for the quantization. So for this part of the project, I think Dorian already gave some background, but to summarize once again, the aim is to create some AI models that will be deployed on edge devices placed in the forest, such that when the camera trap detects movement from an animal, if the animal is not a bear, the system should do nothing. Whereas if we have a bear that is detected by the system, then this should raise the wacky man inflatable guy to scare the bear away. So this means that we had 3 main requirements. The first one was to develop models for low-powered devices and to make them as small as possible. The other one was to work with images that come from camera trap, and this means that they are not professional, let's say, DSLR camera type of pictures. And the other one is that we wish to have, among all the possible metrics for an AI model, a high recall in bear identification. So to solve these issues, we decided to go for a classification model rather than a detection model because they are generally smaller and easier to quantize. And the objective of this classification model is to simply determine whether a single frame contains a bear, any other animal, or nothing. So to do this, we worked only with the Hack the Planet dataset that was given to us. This is a dataset of images taken from camera traps in Europe that contain bears, other sorts of animals, and some frames that are empty. Now you can see from the distribution of the data that we have in the dataset that the empty frames are in much lower number than the bears or the animals. And this has been a problem, slight problem of imbalance while training the models, but I'll show you later how we managed to solve it. Then the other thing was that these images were taken in different locations and different points in time. But this still means that because the camera is fixed, sometimes we would have a lot of repeating backgrounds. Let's say if a bear is passing or if a moose is passing, the background would be the same. And we believe this has created a bit of confusion for the model at some points. So the way we approach this is we try different things and different kinds of models, but I will go directly to what worked. And what we did is appropriate data split to avoid the data leakage. And to do this, we decided to go for a, let's call it temporal split, where we used different seasons for training and for validation, and one last season for the testing. We used quite increasingly aggressive augmentations along the challenge. And in the end, we settled with a pipeline of several transformations that still retain the presence of an animal, as you can see in the image on the right. And to balance the issue, to balance the lack of empty frames, what we did is to have a simple approach of replicating the empty set so that it would balance to the number of images that the other 2 classes have. And mixing this with focal cross entropy in the end resulted in quite good training. We trained different kinds of models and approaches, but here I will present the two that were the most successful. So the first one is very simple. As I said, a single image classification model that, given an image, classifies whether it's empty, any other animal, or a bear. The second approach was to have a pipeline of two models. The first one classifies whether in the frame you have empty or something. And if the frame is not empty, then classify whether it's a bear or not. And the reason why we also tested this approach was because we saw that the model was not very good at picking up the empty frames. And this comes probably because there were a lot of repeating backgrounds, both in empty, animal, and bear images. So to help the model, we decided to try with splitting the problem. So the two pipelines work pretty much well and similarly, with some differences on the same test set. First of all, we can see that the accuracy is above 90% for both of them. This is average accuracy on all three classes. Both models have a very high recall on the bears, which is what we wanted and desired. The main difference stands in the being able to identify empty frames or not. You can see that the sequential pipeline, as expected, has a higher recall on the empty frame. And this also tends to push up the precision on the bear class by reducing the number of false positives, which often came from empty frames that were classified as bears. Now, we are aware of the fact that this has to be put on a small device. So for the following, we will focus on the single model, since they perform more or less the same. But if when this is deployed, the sequential pipeline wants to be tested as well, it can be considered as one option, as it performs well and reduces the number of false positives as well. To put these models into the edge devices, we have to do a process that is called quantization. Now, as I mentioned already, this was mostly handled by Jesse and Gaspar, and they will show more details on this in their presentation. But in very, very few words, what this means is that there are some algorithms to try to make the model smaller by generally reducing the bit precision. This means that the efficiency goes up, but by reducing bit precision, accuracy also tends to go down. There are some newer methods that can use part of the training set to try to maintain the accuracy on the images. And these are the last results that we got. And the quantized model loses roughly a 10% accuracy overall, and manages to still have decent, but still not ideal performance as the original model. More details on this would be in the further presentations. So to test the model, what we did is to use some videos, and not only we used the videos from Hack the Planet, but we also went on YouTube and looked for camera trap videos that would contain bears or animals from the northern hemisphere that would more or less. So what I found was two videos, one from Yukon and the other one, I can't remember the place, but also from North America. But at least the bear population should be similar. So you can see from these few clips that the model is generally good at identifying bears. The bars that you see moving are a histogram of the last 15 predictions, 15 frames at every frame. So to give a more complete view at every frame of what has been predicted before as well. So this is good. And qualitatively, we see that the model finds the bears, both in daylight and nighttime. One thing that I noticed is that the model is pretty good with moose. I guess this is because there are quite a few in the data set, and both in daytime and nighttime, it tends to work pretty well with this big animal. Where it doesn't work as well is with smaller animals, where it usually needs the animal to come closer, and then it is correctly predicted as what it is. And this works with medium-sized animals. In the videos that I downloaded, there were a few clips with very small animals, like a raccoon or an owl, that I believe were completely absent from the original data set. And in those cases, the model was not able to pick them up. And yeah, this thing of the animal being classified when it comes closer, I believe might also be due to the resolution, since for the mobile net that we picked, we reduced the resolution to 200 pixels from the HD that was the original size. One interesting thing that we noticed is that when the bears stand up, they disappear from the prediction. So I guess because the model confuses them with trees, or because there are not many instances of standing bears in the data set. But this is something to keep in mind, and maybe to augment the data set for the future might be considered to have more clips of bears that are standing. Lastly, again, probably due to the composition of the data set, we noticed that the nighttime images tend to have a slight bias towards the bear class. And this means that the model is often a bit confused whether there is a bear or not until the subject gets fully into the frame, where then it usually can identify pretty well whether it's an animal or a bear. So to sum up what we did here, we developed an AI model to detect the presence of bears in camera trap frames. In the end, we settled on MobileNet B3 Small, which is an architecture that is already existent in the literature. And with this, with a single model pipeline, we managed to achieve average accuracy of 91%, recall of bears of 93%, and a false positive rate of roughly 12.4%. Also, by checking how the model performs on camera trapped images coming from a slightly different setup, we noticed that the bears were rarely missed, and so this is a very good point. We found that when bears stand, there are some issues, but also that other animals are generally well recognized, so the false positive rate is not that high. For future steps, what could be done based on what we have learned here is that, of course, as always, data is fundamental. So including more animal species could help in the detecting also other animals that were not present in the original data set. There's this thing about the standing bears, and adding a higher variety on the backgrounds could also help, since we found that there were a lot of repeating backgrounds already, both in each of the three classes. One idea could be to try to separate also day and night images into two models. This is not something that we have explored, mostly due to lack of time, but it is something that might be worth considering for the future. And lastly, the last step is to design the algorithm that, based on the predictions of the AI model at each frame, determines whether to raise the Wacky Man. And as an example, what I think could be useful to do is to look at the distribution of the predictions from the moment that the camera starts recording to the end, and then develop some strategy there. This is not something that we have studied, because I believe the people from Hack the Planet or from BearID are more expert in designing this kind of thing. based on their needs. So that's it. Thank you very much, and I'm open to questions.
Thank you very much, David. Very cool presentation. Yes, let's hear it for questions.
Well, to start, I just wanted to thank you and your team for this effort and helping us, keeping bears out of villages. So these results all look very promising in terms of augmentations. I was wondering, I noticed like the black boxes that you added in the background. Did this really help in removing some of the background bias?
Yes. So this is a technique that is often used to augment images. It's called a cutout. And by doing this, you remove parts of the image that randomly. And by doing it several times, in the end, it kind of averages, but it makes it harder for the model, and it reduces the pitfall of focusing on non-important details.
Yeah, cool. And in terms of hardware, were you able to? I was missing maybe some metrics in terms of performance on how the model performs on hardware. I believe that you might have had access to some virtual hardware environment where you could do some tests.
Yeah, so this will be mostly talked about in the following presentation. So I personally did not work on this, and deployment on Edge team mostly handled that part. So I believe in their presentation there will be more details on the performance. But what I can say is that the model was successfully converted into TensorFlow Lite, and it was relatively easy to do so. And they also managed to use the NXP acceleration, NPU acceleration.
Cool. So maybe just a quick update from my side. I'm happy to say that on the hardware side of things, the system is totally finished and ready to go for our first deployment in the end of May when we're traveling to Romania. So I'm looking forward to integrating this model onto it. Thanks a lot.
Really nice. Cool. All right. I have one more question from George.
Yes, David, thank you. This was a really interesting presentation. I just wanted to ask, how did you define the model? Do you use the TensorFlow APIs natively? Do you use some wrapper around the TensorFlow APIs?
To train the model, we used the latest version of TensorFlow, I believe 2.15, that already has the MobileNet v3 small architecture in the framework. So we initialized the model with the ImageNet weights, and then we fine-tuned from there. Being a relatively simple classification, usually it would overfit relatively quick. So 10, 20 epochs were generally sufficient, and then it would start to really overfit too much.
Nice.
Thank you.
So, yeah, everything that Davide said about the data set and the problem space still is true, holds true. I just wanted to share a quick update on another approach I took on bear detection for Hack the Planet people. So the main issue that we realized we had was the repeating background on camera traps, because of course camera traps don't move. Maybe with seasons they change a little bit because you have snow or like more leaves and so on. So we needed a way to basically get rid of that background noise. And one way to do that efficiently is to actually use an object detector instead of doing like classification at the image level. So that was what I was trying to do with it. And in order to actually balance out the data set between the two classes, which are either there is a bear with a bounding box in it, or there is an animal or an empty frame. So I group those two classes. So basically I get down to like a very simple binary object detector on camera trap pictures. And in order to balance out the data set, what we can do, we can use some data augmentation techniques. So the one we used was the 10 crop augmentation that is presented here to basically upsample the data set for an object detector to really train on a balanced data set. And what we did then was to train a YOLO V8 model on it, an object detector at different image size to basically have a trade-off between precision or like recall and speed. And you can see like 3 models here that we trained. So it's almost like at an image size of 1024 pixels. It kind of runs at 1 frame per second on a Raspberry Pi 5. I checked that with Hack the Planet. So it's not super fast, but it's super accurate, almost like perfect scores. So what we decided to do then is to decrease the image size and see basically the trade-off we're making when we want to run it faster. So with an image size of 320, we can run like 5 times faster on a NeuroPi 5, and we don't really lose much on recall and precision here. So that was a good sign that we could still go down in terms of image size. And with an image size of 160, we kind of moved from 99% of true positives to 96. So we kind of lose a little bit of recall here, but the trade-off here is that we can run it 10 times faster, which would kind of average out because we make predictions on a sequence of frames. So we'd still catch the bears on the video. Yes, that was I wanted to add. That object detection works also really great.
Cool. Thanks. Yeah. So thanks for the addition. And then we can continue for the face detection and face segmentation team.
Well, I guess I should also do it this one. Let me share my screen again and open the presentation. All right.
Yeah, perfect.
So let me present this like this. Okay. So face detection and segmentation. So this is the work that was conducted for the BearID project. It's one small step in the overall pipeline to identify bears. And the idea with this sub-team was to actually retrieve the bear heads and remove the backgrounds or like segment out the actual shape of the head. So this is basically summarized with this picture here. So we get an input of a camera trap here with a bear on it. And the idea is to localize its head and remove the background, like the waterfall and the forest around it. The dataset we got from BearID contains around 3,300 bear images. And they provided us with a bounding box for the heads of the bears and some facial landmarks. So the eyes, the ears, the nose. And we realized that the bounding boxes were often like incomplete. Mouth and ears could be missing, for instance. And sometimes the facial landmarks, the ears and nose are not very accurate. And we decided then to relabel that data set with our own bounding boxes. So we use something called RoboFlow, which is an online tool to quickly annotate a data set. And the whole team collaborated on this annotation effort. And we were able to actually annotate it again, like the full data set, which would lead us to build a very strong head detector, bear head detector. The problem is that we want to segment the full head, so we need to get rid of the background. So to do that, we need to combine it with a way to localize the bare full body. And that's when we could use tools like Grounding Dino or things like SAM, which is the segment anything model from Meta, which would let us basically retrieve the segmentation mask from the pictures. So this is basically what we were doing. So we had basically the ground truth data set from RoboFlow that we annotated with the bare heads, with SAM and the facial landmarks provided by BearID. We could basically retrieve the full body of the bears, and combining the two, we could get like the segmented heads. That way, we built a train set for our bear head segmenter that then we decided to train. So this is some results of using SAM and landmarks as inputs, facial landmarks. So you can see that SAM is pretty good at retrieving the bears when prompted with facial landmarks. And we also tried it with prompting it with bounding boxes as well. It seems to work really well as well. When it comes to the results, so we trained a couple of models. First, we trained a bear face detector just to make sure that the YOLO architecture could learn from the dataset. We also trained another facial landmark based on the provided landmarks by BearID. And then we finally built a bear face segmenter using the dataset we built with SAM and RoboFlow. So that's the baseline results, I guess. No, that's the actual results. So as you can see here, with the precision recall curve, we get almost perfect score. So the model is really, really strong with only like 2 epochs of training. Same with facial landmark detection. But the one that's really interesting is the bear face segmentation. So we trained for much longer here, and we get like a perfect, almost perfect precision recall curve using intersection over union metrics. So that tool basically led us to build a chip generator that takes an bear image as input and can output those little guys, those little faces, with just the head segmented out. That would be then fitted to the bear identification team. And that would sit here in the overall pipeline. So the work of that team actually focused on the two, like the first row here, top row. Any questions?
All right, thank you, Arthur. I'd like to continue straight to the identification team. I think that links well to this presentation, and then we'll keep the questions for after that one. But thanks very much for presenting. Who can I give the word for the identification team?
Yes, I will present it.
Perfect, thank you.
All right, so the bear identification team indeed follows on the segmentation team. So this is the pipeline that we created. So the upper part is what Arthur just explained. So from a bear image, we go to a segmented face, and that face we embed using a embedding model into an embedding space, and we compare those embeddings to see which image originates from which bear. So the approach we used mainly was metric learning. And metric learning learns a distance function which focuses on distances between similar and dissimilar data points. So similar data points must have a very low distance, and dissimilar data points a very high distance. And using that metric learning approach, we can find k nearest neighbor embeddings, so k nearest neighbor bears. So about the data, we identified 3 different options for a data split. So the first is closed set. Then you only can identify individuals that were in the training set, but that was not useful for this case because we also want to identify unknown individuals. So that one we don't use. Then you have open set. That is, you can identify both seen and unseen individuals and identify them. And we have the disjoint set. So that is a test set with completely new individuals. So no individual that is in the testing set also appeared in the training set. And we used the last 2, so the open set and the disjoint set. So the architecture, well, the high-over architecture we used looks like this. So we have input image channels times width times height, which is fed into a pre-trained CNN backbone. So I will cover the exact types of backbones later. Then that model outputs feature tensors, and those tensors are fed into a fully trained, fully connected layer. So essentially, we stripped the classification part from the CNN model and replaced it by our own fully connected layer with without pre-trained weights. And that outputs then the embedding vector of dimensionality D. So metric learning is like a general approach, but you have multiple metric learning loss functions. The 3 loss functions that we used were triplet loss, circle loss, and arc phase loss. So triplet loss compares an anchor with a positive and negative sample. Positive sample is from the same class, negative from a different class. Circle loss uses a positive pair and a negative pair. And that is, circle loss is different from triplet loss because it can really make a trade-off in loss contribution between positive and negative pairs. And arc phase loss is a loss function that is really designed for identification purposes. It's a bit complex to explain, but it's designed to enhance discriminative capability of the features outputted by the model. So essentially, the goal of metric learning is this. So you have a original data space, and you want to end up in a space like this. So different classes are apart, and inside the class, they are stuck together. So the dataset that we used initially contained 4,000 plus images of 132 bears. And in the last 1 or 2 weeks, we got access to an extended dataset containing images originating from camera traps, which increased the size to over 50,000 images and 144 bears. Before we feed the image into the model, we have some very basic steps, some pre-processing steps, just to increase the robustness of the model. So we want it to be robust for like rotations and difference in lighting. So we resize, we apply color jitter, we slightly change the hue and saturation and do some random rotations. And here are some results. So in the left column, you see the different types of training sets. And you see that the ConvNeXt large backbone with arc phase loss is performing pretty well. 95.5 precision at 1, so that means 95.5% of the images, the embeddings are close to an embedding of that same bear. So that's for 95.5%, and then 96.5% of the top 3 images contains an image of that same bear, etc., etc. And in the image below, you see the reduced embeddings. So these, of course, the dimensionality is reduced to 2 to be able to plot it. And you see as the epochs, so during training, the epochs increases, you see really the clouds of embeddings of different individuals are very far from each other. And inside the clouds, the points are really close together. So that's exactly what we want. And here are some more results on the disjoint set. So previously, I showed the ConvNeXt large model, which has 198 million parameters. But of course, efficiency, as already mentioned, is also an important factor. So we also used ConvNeXt Tiny, which only has 28 million parameters. And on the camera trap extended dataset, it achieved 93.8 precision at 1. So for such a small model, that's pretty good. And you see, also a large difference with other backbones, such as ResNet and EfficientNet. So some example outputs. So here I generated embeddings for every test, so every image in the test set. And then for each image in the test set, I do a nearest neighbors search for 3 neighbors. And you see that for this specific bear ID, the top 3 are all originating from the same bear, so from the same individual. So this is a good example of a correctly p at 1 output, and this is an example where it was wrong. So yeah. So the key findings were to use hard example mining. That means that during training, you essentially search for the pairs that are currently the most wrong. So, for example, positive pairs that are very far apart, which is, of course, not what you want. And, for example, negative pairs that are really close together. And doing that sampling, it decreased the performance. Also, we saw that the extended data set increased the precision by a large margin. So yeah, more images per individual really benefits the learning. More individuals, but not more images per individual, probably makes it harder. Also setting up an environment to quickly compare different backbones, losses, samplers, etc. So really all the different configurations is also very good, because then you can really quickly focus on the most promising techniques. Also, we saw that using different learning rates for the CNN backbone model and the embedding layer is also very good to do. Because yeah, the pre-trained backbone is already trained pretty well, so that can stay more or less the same. And it's really, the power is really in the final embedding layer. So that needs a different approach. So we also experimented with loss functions. We started with triplet loss, which is really intuitive and also widely used. Then we went to the circle loss, and then really the specific arc phase loss. And also, of course, random hyperparameter search is key to find the best hyperparameters. So there are a lot of hyperparameters, learning rates, output dimensions, etc. So it's really really nice to do a hyperparameter search to find the optimal hyperparameter values. So some limitations to our findings are that we didn't do k-fold validation. So we didn't split into K folds and used one of the folds as test set each time. And also in the test set are relatively similar images. So yeah, that of course is quite easy for the model to be good at. If two images are visually very similar, then the model can also find the same individual pretty easily. So we didn't account for that. Then Anton also did some experiments using a mega descriptor, and that is a foundation model for exactly this task. So for animal re-identification, but of all sorts of animals. I don't know how many, but multiple species. And it is a pre-trained SWIN transformer architecture. So Anton also used that model for this task. So what he did was like doing 0 shots, so not training on bare photos of our own data set. And with different model configurations, that led to 75 up to 85% top 1 precision. So without even fine-tuning on our data set, that's pretty good already. And with some transfer learning, the tiny model achieved 90.5% top 1 accuracy. And the larger model, which is almost 10 times larger, achieved 92.5%. Also, a user interface was made for doing predictions, so you can very easily see the output of the model. So here you see some example outputs, which also made it very convenient to do some experiments. I don't know if you want to do questions now or at the end.
Thanks, Simon. Yeah, we can do some questions now. Also, quick question: is it possible that we quickly show the UI, or is that?
I can show it currently, so unfortunately.
Okay, then maybe we record a short demo about that, and to be able to share that as well. That would be very cool.
Yeah.
Thanks so much for the presentation. Amazing results, I'd say. 95% top 1. That's more than I hoped for at the start, to say the least. But so really good job, guys. Are there some questions? I don't see any in chat, so otherwise we continue to the last team.
I have one short one. So I saw that you trained both the COVNEX Tiny and the COVNEX Large with the additional data set, and you explicitly mentioned that this really increased the precision. I understand this was not on scope for now, but do you think that the precision of the ResNet and EfficientNet would have grown to a similar margin, or do you really think that this backbone is just a lot better? The COVNEX backbone is just a lot better than the ResNet and EfficientNet for this specific problem.
Yeah, so if you see the results with the initial data set without the camera trap images, you see a relatively large margin between ResNet and COVNEX. So I think that it will increase the ResNet precision, but I don't think that it will be a very that it will be similar to COVNEX. I think that backbone is just way better.
Okay, cool. Lastly, I can concur what Dorian said. Really amazing results. I would not have expected us to be this precise in the 10 weeks. So congratulations on you and your team.
Thanks.
Melanie.
Thanks so much. Thank you, Simon. That was great to hear, and super exciting results. I'm really looking forward to kind of digging into this further as well. A bunch of different questions came to mind, but obviously we don't have time to go into them all now. But I was just wondering about the different splits in terms of the disjoint set versus the open set. I think you had a slide that kind of gave an overview of the results of the two, and I think I noticed that the open set was quite a bit lower.
Yeah.
So I was just wondering, I was quite surprised about that. I would have expected the opposite. So I just wondered what you thought about that.
Yeah, we were actually very surprised too, because we expected indeed the opposite, because yeah, it seems that open sets, so individuals that it has already seen, should be easier.
Mhm.
So yeah, I must say I'm not sure why it performed worse, but it was the case. So for this ConfNext large, but also for Mega Descriptor, it was also worse. So yeah, it's
Interesting.
just guessing, but I couldn't say why.
Yeah. Okay. Yeah, that's interesting. The other thing I just wanted to kind of mention was about, and you talked about this at the end, about the limitations of having a lot of clusters of images that were perhaps from like the same camera trap video with our camera trap data set that we added, but even with the still images, we have some photos that were, taken in bursts from the DSLRs. So I'm just wondering if you have, I know you say it possibly inflating the precision. I'm just wondering if you have any idea or inkling of how much that could be having an impact on this. I mean, I know that's a hard question without actually maybe just pulling one image per sequence and running it again and seeing how that's performs.
So I've been thinking about how we could like solve this, and I didn't try it because I didn't have time, but I can imagine you can use like metadata and like see the timestamp and pick one, for example.
Yeah.
That could be a solution. I believe I tried some very naive method which discarded too much images, and that caused like the data set to shrink too much to have a good precision number. So yeah, we experimented with it, but in the end it was for us too hard in a short time to fix it.
Mm-hmm. Okay. I guess also with that hard mining approach, it should focus on the more different images. Is that correct? Rather than the more similar ones. So those from a sequence obviously will be a lot more similar.
Yes, but yeah, to be clear, that is of course during training. Then during testing, if you have like, let's say 10 images that are really similar, then of course the model has a really easy time. So that's why the precision metric might be a bit artificial,
Mm-hmm.
but to what extent, I'm not sure.
Okay, great. Thank you so much.
Gaspard.
Yeah, really simple question. Which frameworks did you use for training, and did you use different ones per model, or did you just stay within one framework?
And with frameworks, I guess you mean like PyTorch, TensorFlow.
Yes.
Yeah, so for all our experiments, we used PyTorch, and specifically we used the PyTorch metric learning Python package, which offers like very easy mining functions and loss functions out of the box.
And then did you test the model in your own environments?
What do you mean with the environment?
So your own programming environment, so that you inference it and then assess its performance.
So yeah, I think some people use like the GPU machine offered by Fruitpunch. I use Google Colab, so I think those two.
Okay, so it was necessary to do it on a powerful machine.
So not necessary, but with limited time, it's good to have a GPU because it's sped up the training and yeah, exactly.
Yeah. Okay.
Last question, Peter.
Yes, I would like to get back to Melanie's comments on trying to estimate the possibly inflating the precision metric. So if we go back to the table where we compare the disjoint set with the open set, maybe I can explain you the different evaluation strategies we have here. So on the disjoint set, we basically use the test set as the query and the reference and the gallery. So which means that we can see the inflation when there are like many similar images. It's very easy to have like a cluster of embeddings which are close to each other. But with the open set evaluation strategy in this specific table, we actually replicated the work you guys did with Ed by using the the test as the query, but using the gallery, it would be the train and validation sets. So you can actually measure how much inflation you get by comparing those two metrics here.
I see. Oh, okay. Thank you for clarifying that. I don't know if Ed has any comments in relation to that, if he's on here.
No, I had a few exchanges with the team during the process, so I'm glad to see these numbers are on there for comparison. I think, yeah, we need to work on a disjoint set that has, also reduces this leakage, because I think it's very encouraging to see these kinds of numbers from the disjoint set, because that's ultimately what we'd like to achieve. But yeah, we need to think about how we test this without using some of those images that are so similar.
Right. Okay, then we can head into the last team. We're already going a bit over time, but I still want to take the time and the attention to listen. I think Gaspard or Jesse?
Yes, I will start.
Awesome.
All right, so that brings us to the last presentation, running the pipeline on Edge, where Gaspar, Paul, and I have mainly been working on. So the goal was to have the entire pipeline work on the chip that we used as efficiently as possible and with the highest performance as possible. So we used the IMX93 by NXP. And here on the slide, you can see some specs. So 2 GB system memory, 16 GB storage memory. But the most important spec is that it has an NPU, which allows to efficiently perform operations that are used in machine learning algorithms, like matrix multiplication convolutions, by accelerating these operations. And more importantly, these tasks can be performed with a lower power consumption compared to using the GPU or CPU. So this can be very beneficial for our use case, as we want to, as you call it, the balloon man as quickly as possible. But we also want to ensure that the chips work as long as possible without having to be recharged. So having a closer look at the inference using the NPU, it can be seen from the figure at the right that the NPU is specifically supported for the TensorFlow Lite library, which actually brings us to the main task and difficulty of our team, which is having all the models converted and working in TensorFlow Lite, since most of the models that have been trained have been developed in PyTorch. Usually problems can occur with the conversion, like operations not being supported. So this is the pipeline that we have been using, which has already been explained a few times. But the 3 different parts of the pipeline, which are numbered here, are the ones that use machine learning models. So these are the parts of the pipeline that we have been focused on. So the bear detection, generating the chips from the bears, and then performing the bear face matching. And one important consideration to make is that if we do not use the bear detection and we run the algorithm, it is possible that bear face is detected in a non-bear entity. But this is not really a problem for the use case of Hack the Planet, since they do not perform a bear identification. But we do need the bear detection for the Bear ID project use case, as otherwise the pipeline would be ran sometimes, possibly, without there being a bear, and this necessarily consumes power, which we are trying to prevent.
Yeah, at this point, I will tell a bit more about kind of the figures that we found and the things that we tried. So in our previous presentation, we already kind of showed that we tried to convert a light glue model, which now was, I think, not mentioned anymore in the presentation, so probably discarded. But this showed us that indeed some operations are not supported in both the conversion from PyTorch to Onyx or ONX and then to TensorFlow, because these both need to match if you want to do an automatic conversion, and otherwise you need to completely write a new operation from scratch. So the conclusion is that sometimes converting PyTorch models to TensorFlow is not directly possible, or it will require some manual fixes. But also in a blog from ARM, we found that, and this is something that we will also show, which is reflected in our own experimental results, is that if you convert a model from PyTorch to TensorFlow, then the NPU cycles remain more or less the same, but your CPU cycles will increase, and also your inference speed will be higher than if you natively trained a model in TensorFlow. It's, in this case, in this table, you see almost 6 times higher. Yeah, next slide, Jesse. So here's the juicy part. These are the results. We didn't have much time to actually assess the performance of the detector model, but we did look more closely at David's classifier. And in bold, you see the important parts, which was where we ran it on the NPU. Now the recall goes down quite a bit after quantization, although the accuracy is a bit higher, as David also showed. But the inference time is amazingly short, which is what we want. And this is similar to what we've seen in other people that have ran similar models on NPU. So this is what is to be expected, and this is super efficient. Also, we looked up an estimated power use in the documentation of this chip, because we didn't yet test it on the experiments we ran ourselves. But this is this figure, this amount of watts, is from also a similar model which was run on the NPU, which takes only 0.86 watts. So these are, of course, important figures if we want to determine our battery capacity, which is needed if we want to deploy these kind of chips in the field. Now the detector, we actually only were able to convert it today, so we didn't have time to assess its performance. Which is maybe good to mention is that the classifier, we converted it using our own pipeline and TensorFlow libraries, but the detector and segmenter, we converted it using a toolkit from NXP, the EIQ toolkit. So that's something that we were not able to use previously, but we got our hands on it finally, and we did make a conversion. So we tested that, and you see it's quite a bit heavier than the classifier, 300 milliseconds for inference time, but it's very positive that it can also run on the NPU, which means that you will have lower power consumption. And to kind of make a comparison with other kinds of chips, we did also run the same classifier model on a Raspberry Pi 5, where you can see that it took six times as long to inference the same quantized model. And we also had a look. I also had a look at the specific chips power consumption to get an estimate of the power draw, which is not crazy much higher, but it is definitely higher. And of course, with your increasing inference time, this will also increase the battery capacity that you need. And just for comparison purposes, we also inference these models on the CPU of the IMX93, but that is not a thing that we would recommend. If you look at the figures, it's absolutely not meant for running the models. It's simply meant for how you say, like for giving you the environment to set up your application, but it's not meant for actually inferencing the models. So that being said, we did not test the conversion of the ConvNet model to TensorFlow, but it would absolutely be necessary to run it on the NPU if you want to use this IMX93. Otherwise, it kind of defeats the purpose of using this chip at all. So next slide, please. There were some things that we still should try, that we were trying, but we didn't fully succeed, which is you can quantize-aware train models such as the MobileNet, which means that once you quantize it, you don't get such a loss of accuracy, which you can also see in this table, which we have from a TensorFlow documentation or a blog. However, even within the TensorFlow framework, we ran into some issues with some layers not being supported for quantize-aware training. So we ran into a known issue, which has been an issue for a while, and it has not been solved. But yeah, it probably can be circumvented with a bit more research. So that would be a next step to take. And then, of course, measuring the full power consumption of running the full pipeline once all the models are converted, which includes also having to convert the feature matching algorithm. So this concludes our research.
All right, thank you so much, Gaspard and Jesse. Great work. I know we've saw a lot of hurdles, but I think you guys really pulled through and great effort. So thank you so much. Let's see if there are any questions.
I have one. If you can go back to the one including the power consumption, just to clarify on my end. So that is a measurement in watts of the chip's NPU specifically, of the entire chip when the NPU is activated, or?
That's of the components that are drawing power when you are running the inference.
Okay, so
so it's not so this excludes. It's a good question because it excludes the power that it's drawing when you're idling the machine.
Yeah.
And for example, I did look into this, and I know that the Pi 5 can be very efficient in idle time. So that's good news for the Pi 5. But I assume that the IMX93 also has a very low power leakage when it idles.
Yeah, likely. And then one more thing, I guess that's also a comment just to clarify this. It looks here like the IMX or the MobileNet and the YOLO V8 model would use the same amount of power because you expressed it in watts, but you should multiply it by the amount of seconds, obviously, to really get the power footprint, right? So it would be almost 150 times more power consumed from your battery when you use the YOLO V8.
Yeah, exactly, and I think if you would retrain the YOLO V8 in TensorFlow natively, judging from the other research that we saw, the slide that we showed before, you could reduce it by a factor of 6. You could divide it by 6 the inference time.
That's amazing, really nice. Yeah, great work. I also know there were a lot of hurdles, but you guys plowed through. Thank you for that.
Otherwise, there's one.
Yeah, hey, Eric from ARM. Awesome work overall, really good results overall. Wonderful to see the ARM NPU executing and doing its job within the IMX platform, and then some. So well done. Just curious if, and I'm sorry if you mentioned this already, I may have been paying attention to something else. how do the virtual models play into your workflow at all, if at all? Were you able to use them? Was it kind of an aside at this point, given your time constraints?
Do you mean the virtual hardware?
Yep.
Yeah, no, that was definitely useful because we were waiting for the actual evaluation board to arrive, so we could already kind of get a feel of the environment of the chip. Because yeah, it's a good question. And Sako mentioned some hurdles because yeah, for example, we also as you see in this table, we also just tested for the heck of it if we could install Torch on the IMX93 and inference with Torch, but of course it's not supported, and you see that the inference time is crazy high. But yeah, definitely like the virtual hardware was very good to kind of get a feel of like what kind of Linux environment are we working in and what is possible, what are the resources that we have at our disposal to actually get this thing on chip and in the field.
Okay, cool. So it sounds like the main benefit was kind of giving you something to play with and develop on in advance of getting boards. If you wouldn't mind, I would love to follow up with you offline, just do a little bit of a debrief and get any critical feedback as well, and just maybe explore some other ideas we have for the use model for AVH that you might not have been able to employ this time around, but I'd really welcome your advice and opinions on some of that stuff. So
yeah, sure, happy to do that.
Nice. All right. Thanks. Could you close the presentation? Yeah, that already brings us to the end. If anyone would like to rewatch anything and comes up with any questions, feel free to reach out at Melanie Thijsjerol in Slack. So we'll also still be available there for any questions that come up. The report will be delivered next week somewhere. The participants will get 1 extra week after the final to finalize all the results and make sure that everything is nice and readable. The code as well. So yeah, documentation. On documentation side, there's still plenty to happen this week. For the participants, you will receive a peer review as well during this week, which you can fill in, and that will be used to create your certificate at the end. So please take some time to fill it in carefully to make sure that all the team members you worked with get the skills that they deserve. And that said, I'd like to open the floor for Ed and Melanie first to say some final words.
Yeah, I don't know. Ed, do you want me to go first, or I don't mind?
Sure, go ahead. I was having a hard time finding the mute button.
Yeah, I just want to finish off by saying thank you so much to everybody. Like, so much time and effort has gone in over these past weeks, and just really, really appreciate everybody's time on this, and really look forward to digging into the documentation and the report. And we're just at the start of field season. The bears are just waking up over here, so it's a fantastic time to be able to trial some of these models actually out there. So I was going to ask about, and I don't know how long the Slack continues, but I'd really like to be able to keep everybody up to date with like how we're using these models if people are interested. So I'll speak to Dorian and Sako about that and figure that out. But I'd really like to provide that feedback to everybody about how we're using these models and if we, further develop them. And if anybody's interested to continue, to work with us, then please get in touch. And thank you so much, everybody. Really appreciate it.
Yeah, I want to second Melanie, thanking the team and the presenters here today. The results are great. Very encouraging to see what you guys are able to do in a relatively short time. I've obviously tried out the detection and segmentation model when I ran it through all the video to create the video chips for the extended data set, and I was pretty pleased with how easy that was to use and how well that worked. So looking forward to trying out some of the rest of these models. And I'll be presenting about this challenge at the Embedded World Conference next week in Nuremberg, Germany. Looking forward to getting some of these details from your presentations today to put into the slides that I'll be presenting there. And yeah, thanks again, everybody, for all the great work you've done.
Thank you so much for these kind words. It was a pleasure working with you. And then to finalize everything, Thijs, do you want to say some final words?
Yes, it's almost dinner time here in the Netherlands, so I'm getting pretty hungry. No, just joking around. I think I'm also really pleased with the results. The work that has been done is amazing. I'm cannot wait to try out the model that you've trained. I do want to give some special thanks to Arthur, who in between his work of the other team reached out to me and started work on the YOLO model that I currently have on the prototype that I developed. I've posted a video in Slack of that system that we're going to deploy in Romania, and in the upcoming 2 weeks, I will be evaluating both models, the one from the YOLO model and the other model, to see which one will give us the best results in terms of performance, not overheating my hardware, and accuracy. So that's going to be really exciting, and I do concur with what Melanie said. We will be deploying these systems in May in Romania, and I would love for you guys to see that all your sweat and tears and effort is not wasted and will actually be used in the field within a couple of months.
That is great. Yeah, that's really awesome to hear. I'm really looking forward to see those results. Feel free to reach out to us at any moment, and then I'll be happy to set up or at least forward all your interesting videos to the participants, or maybe post something about it. But that said, big thank you, everyone. This concludes the challenge. We have 1 more week to finalize the report, but I really want to thank everyone for the last 10 weeks, for the hard work that you've put in. I know that a lot of you have full-time jobs beside this, or full-time studies, so it's I really admire the effort that everyone has put in. So big thank you to you all, and I wish everyone a very fruitful evening.
Thank you,
Thanks,
guys.
everyone.
Thanks so much,
Thank you.
everybody.
Thanks,
Thanks again.
Bye, everyone.
Bye.
Ciao, ciao.
Bye-bye.